Yes, for the Harpoon mechanism or approximate Rx value, which is at the maximum distance from where electron can be transferred from uh, potassium to bromine molecule. Right. So that's what we are discussing. Now that calculation can be done for the approximate value of Rx using the uh, relation. If we equate at the crossing point the covalent potential, sorry, ionic potential, this going to be equal to the uh, covalent potential, right? So that is van der Waals forces. Now, if you look at this curve, this when this potassium is potassium plus Br2 are neutral, then there is very weak interaction, which is covalent interaction, that is going to be 1 by r to the power 6, right? And this value on the right hand side is very small when we are at the asymptotic region and coming closer even at the crossing point. So what we can do, we can neglect that part with respect to this. So that means we can equate this to 0 right hand side, right? So if we equate this, then the from this relation we can get the approximate Rx value. So that is Rx is going to be uh, this this divided by delta E, right? So that is E square divided by 4 pi, then epsilon 0, and I am going to have delta E 0. Right. Now, this E is of course like electronic charge, so that is positive and negative. So if we can get this value, get this relation work it, so approximately we can get this Rx value, right? So that's what I think I showed in the previous class. So that is basically this one, right? So and here we are taking this 1 by 4 pi epsilon value, that is this approximately this value. So depending on the like epsilon 0 value, you can calculate this. This is going to joule coulomb inverse 2 and meter, right? Now if you replace this in that in this relation, right? So approximately this value you are going to get something like 14.4 divided by delta E 0. If you put it in this in electron volt and convert this, then you are going to get something like in angstrom, right? Once you know the Rx value, you should be able to get the reaction reactive cross section value for the Harpoon mechanism, what is going to pi Rx square, right? So that's what is we discussed in the last class. Now if we I think Binoy sent me one problem which was somewhere in the net exam. So let me put it here and we will be able to work it out. It's a very simple thing if you know exactly what they are talking about. Okay, so that is this one, right? So for the reaction which we discussed already, so that is potassium plus bromine 2 is going to give you the KBr plus Br. It's following the Harpoon mechanism, and they are giving you the data. Use this E square by 4 pi epsilon is 2.3 into 10 to the minus 28 joule and meter, right? Now ionization energy of potassium is going to be this. If this is a, look at only thing you have to remember, this is in kilojoule, right? This is in joule, so you have to convert the unit, right? That is the idea. And then you have electron affinity in kilojoule per mole. Now look at here. Here we put the electron volt, and so therefore the per mole conversion we really don't need it. But in this case it is per mole, so you have to convert into per molecule and then do the calculation, right? So that sort is the idea. So now if you do this, so the relation is then is going to be like, it is going to be Rx is going to be this value. So that means 2 point yeah, so that is like I'm just Rx is equal to, now that is going to be 2.3 into 10 to the power minus 28. Now this divided by delta E. Delta E is nothing but this minus this. So if you subtract this value, that comes around like 172.5. Right. So try to do it. You should get 172.5. Right. But that is in kilojoule. So if you want to convert into joule, because you have to, so this is going to be your joule and then meter, right? Now this is actually kilojoule, so you have to convert into joule. So multiply with the 1000, right? So therefore this is going to be converted into now joule, and then it is mole inverse, right? So that is going to be mole inverse, right? Now to make it in the unit of distance, what we have to do, this joule is going to get cancelled out now, and then this joule going to get cancelled out. Now mole inverse is there, so that means this is per mole. So if you want to convert per molecules, you have to divide it by the Avogadro number here. When you divide this, it actually goes up. So you are going to multiply with here 6 into 10 to the power 23. Right, and then that is mole inverse. Right. Now this mole inverse and this mole inverse gets cancelled out, so you have in the unit of meter, right? And that is something like comes 8 into, you can work it out, I should be getting this 8 into 10 to the power 10 to the power minus 10 meter. Right. Then you apply this formula Rx sigma r, so that means reactive cross section, which is basically pi Rx square. Then you should be able to get the value what you are expecting. So the answer, 4 answers were given like these numbers, right? So one was 15 to 10 to the minus 18 meter square. This, so answer is going to be second one, that is 2 into 10 to the power minus 18, because if you do pi r square, so this is 8, right? And then if you make it square, that is going to be 64, then pi is going to be 3.14, so that comes near about 200, right? Now if you want to make it to 10 to the power minus 18, so that is going to be 2 into 10 to the power minus 18, right? So answer is this one. I think that's what we get it, right? So the answer is going to be this one. Okay, I think yeah. So from this discussion, what you realize is that, like if I go back here, so you should be able to understand that this reaction cross section or the reaction probability, whatever you think about, that is basically, it depends on the potential energy, right? So depends how the potential is acting on the system. Depending on that, we are the reaction is going to be controlled, right? So therefore the if we know the potential energy beforehand, before discussing the dynamic, it should be easy to discuss how the dynamics is going to be expected, right? So that's why the potential energy surface is very important, and we can explain a lot of things based on your potential energy surface. Like if we do experiment and we get some result, right? Now that experiment, there are like I would say the which is not obvious from the experiment. Like if you do experiment, then some of the information, detailed information are missing, right? So therefore you need to uh, do some dynamics calculation and perform some analysis, such that you can explain the observed experimental fact experimental, right? So it's basically complementary. If you do the experiment and then you do theory, and then finally you should be able to come to a conclusion what is going to be the uh, actual dynamics and what is happening in between the reactants and the product. So for that we need the potential energy surface, right? So let me slowly get in. I think I don't know Professor Ray how much he discussed it about the reaction profile and all these things, but here I'm going to give you a little bit detailed description about the potential energy surface. What is the role of potential energy surface on the reaction dynamics, right? Or the chemical dynamics. Okay, so the potential energy surface, if we want to understand, like any dynamical process in day-to-day life or whatever the reaction when it's taking place, it's basically the interaction between the molecules or the atoms, right? So when you say the interactions, so that means there are basically forces between the atoms, and I hope you are used to with this, the forces for a conservative system. Actually, conservative system means the force for a system where the forces between the atoms can be derived from the potential energy derivative of the potential energy with respect to the distance, of course with the negative sign, right? So if we are in a conservative system, then the forces between the atoms can be derived from the negative derivative of the potential surface. So therefore the potential information of the potential is very important if you want to know the dynamics, right? So now when you go for multi-dimensional system, like multi-dimensional is more than two, like if we have two dimension, then it's a potential energy curve, diatomic potential, all of you know quite well. So this is the if we go for multi-dimensional potential, then it is called the potential energy surface, right? So that is behaving like a surface, not the curve, right? So it's kind of a mathematical function which gives the energy of a molecule, whatever the molecule you take, a function of its geometry or the internuclear coordinates, right? So that is gives you the idea. So that means if I give the geometry of a molecule at any point, I should know the what is going to be the potential of the molecule, right? So that is basically the potential energy surface, a mathematical function, right? Now let me go back and show you this curve, potential energy curve, which you are quite familiar with, and we should be able to work it out how the potential energy surface is going to look like. Okay, now I hope all of you are very familiar with this, and if you can recall the quantum chemistry class where we were discussing the Born-Oppenheimer approximation, and I hope you recall that I drawn this curve and asked you that we say this is a diatomic potential energy curve. Now what does this potential mean, right? So this is a potential energy, right? That is this is just energy is written, but this is actually potential energy. We say now potential energy is for the atoms, right? Atom nucleus actually. So if we think about this is H2 system, so that means somewhere, of course this is the scale is going to set anywhere. So I mean, like if you set a zero of energy somewhere here, so that is something like this. Sorry, this will not cross. I think I should erase this. Actually drawing with this pencil is getting difficult. So anyway, but let me now do this. So this is something like the way I had drawn is something like let's say something like this, right? So this is a straight line. Now this value is going to be 0, right? So the way I had shown is like one hydrogen atom here, so that is Ha, let's say, and Hb is coming towards Ha, right, in this direction, and then what is the potential they are going to feel. Now if we do that, this is actually, this curve actually represents the electronic energy with the nuclear repulsion. That's what we had discussed before. So now when we say this is electronic energy, of course you have to remember that this is like electronic motion and the nuclear motion are going to be separated, right? So that is basically under the Born-Oppenheimer approximation, right? So in Born-Oppenheimer approximation, we assume that the nuclei are very heavy compared to electrons, and therefore the motion of the nuclei can be separated from the motion of the electrons, right? So then what we did actually parametrically this distance. So we frozen initially the nuclear distance and then solve the electronic part of the Schrodinger wave equation, and whatever the energy we get, we have plotted this. So that's the parametric dependence of this on R, right? So this potential energy curve actually the electronic energy which acts as a potential when the two nuclei are going to come closure, or they are going to follow it up, right? I hope this you recall this, and based on that, all the potential energy curves are going to potential energy surfaces are going to be discussed, right? So under the born Oppenheimer approximation, we separate the uh, nuclear motion. So that means that is vibration. Actually, nuclear motion is the vibration. We separate that from the electronic motion. So we solve the Schrodinger equation of the electronic motion for a frozen distance or for a fixed distance of the nuclear distance, right? And then we plot one by one, and we get the this potential energy curve, right? So with this much introduction, I think if we think about the potential energy sharp, so that is basically going to be more than two-dimensional plot, right? Here we have two-dimensional plot. One, this is going to be the internuclear distances, and this is the energy. Now, instead of hydrogen molecule, if I consider a system which is H plus H2 reaction, right? So here I am going to think about the simplest triatomic system, and again it is collinear. Be careful, because that depends on the coordinates how it is going to be. If it is not collinear, you will have angular dependence also. So now this is a triatomic system. So that means I am thinking about a reaction kind of like H plus H2, and I would like to know what is going to be the potential when it goes from the reactants to the products, right? Now for that, let me define the coordinate system. Like, okay, now here atom A, so that is the hydrogen atom A. Now here is my H2, so I have given B and C, so this is BC. Right. Now this is reactant because HA is kind of infinitely separated from H2, which is vibrating in the equilibrium distance. So RBC is nothing but the equilibrium bond distance of H2, right? And this is infinitely separated. So that is kind of reactant, right? Now I have taken the liberty that this approach of this hydrogen is collinear, right, to make our system simple, right? And then we will discuss later on how the bending is going to come. So when it comes collinearly, then I have having only two parameters, the internuclear distances, to define the system, and the third one, which is RAC, is automatically defined. This is RAB plus RBC. So that makes my life simple. So I really don't need to restrict this, because it's automatically comes in. So that is basically collinear approach. Now, right. So that is the reactants. Now the products, what I am getting when A comes closer to B, and then this BC bond gets elongated, right, and then finally it breaks. Then finally the products what we get is, again I get H2, but this is now AB plus hydrogen atom C. So this is product. Again, this hydrogen atom and the C hydrogen atom is infinitely separated from this H2AB, right? So it's pictorially like this. If this is color is giving like this, so this blue color is coming with the purple color, then this light blue color is going to go away. So that is the system we are thinking about, and this is of course the collinear approach, right? So if we have this kind of system, now what is the potential going to look like, how this is going to be appreciated, or what is the, when I am going from reactants to the products in between from here to here, how the potential energy is going to be acting on this system, right? So that's what I want to discuss. Okay, so be little bit patient. It's like I think at first instant it's not that easy to understand. Now potential is going to be looking like something like this. Okay, now you might be wondering what is that. Look at here. So this is kind of I'm thinking about, this is my reactants, this place, right, and this is the products. Okay, now this you can look at here, this is A plus B plus C, so that means all the three atoms are infinitely separated, right? So that means A is infinitely separated from B, B is infinitely separated from, and again C is also infinitely separated from A. So all are infinitely separated. So it's you can think about three individual atoms before any interaction. Right. Now this, if you think about compared to this, now A is still infinitely separated, but there is an interaction between B, C. So I am coming from this place. So this is A plus B plus C, and this is the potential energy. Now if I go along this direction, my BC distance decreases, right? But A is still infinitely separated. So that is A plus BC, and now this point is exactly the equilibrium distance of BC, right? Now A is still infinitely separated, so that is my basically reactants. Now if you look at this location, this place, now here it is AB plus C, because again this place is all are infinitely separated, A plus B plus C. Now if I go along this, then A and B are coming closer. This is equilibrium bond distance, this is equilibrium bond distance of AB, but C is still infinitely separated. So that means this is AB plus C, right? So this is products, right? This is reactants, and these are products. Now when it goes from reactants to the products, then there is a potential, is this reaction is going to face the potential, and it goes like this, move like this, and comes here, right? So how the potential is going to look like, so that is you can sort of visualize from this three-dimension figure. Okay, let me just introduce here. This blue curve is like nothing but a potential contour. Contour in a sense is that depending on the coordinates, the potential energy of the system should change. Now these points on this blue curves indicating they are having the same potential energy, right? Whatever the coordinates are. So that means this is of equal potential energy connected for the different nuclear configuration or the geometry of the system, right? So this is called the contours. Now this contour is having higher potential than this one, like this. So these are the potential energy contour. Okay, let's don't get into that right now. Right now what I am trying to just give you idea, So what is this? This is nothing but the reactant. So what I get actually, if you look at like this, so this is now this I have the diatomic potential, right? So this is actually for the BC. So this BC curve, so if I plot, this is the BC distance, A is infinitely separated, right? So something like A is infinitely separated. Then when I comes here, then B plus C also are separated. So this is something like B plus I'm going to have C, right? So as if like I'm having, you can think about B, I am fixing it here. C is coming along this direction, right? And A is still at infinitely separated, right? Now when I move C along this, right, what do we really get? Now this is equilibrium distance or equilibrium distance of BC, right? Now if you can compare this, look at here. So you are here, so A plus B plus C. Now BC is coming closer, so diatomic potential is going to go now at the equilibrium distance, and then coming closer is going up, right? So that is nothing but the diatomic potential what you are going to look at here. Exactly in the same notion, if you look at this products, I've just flipped it around to show you this. Now here is similar to this, but this is actually for the AB molecule, right? And C is still infinitely separated, right? So this is again, if I do this, so this is for the AB, right? And C is still infinitely separated, right? So initially we have A plus B plus C, right? So this part is basically something like, if you think about, I'm here now, AB distance is getting reduced. Now I'm at AB equilibrium distance, and then it's going to go up, right? So that is basically this one. So this is the diatomic equilibrium distance of AB plus C is infinitely separated. So as if like we are going from this reactants to the product. Now when you come in between, of course all of them like A, B and C are interacting in between zone, right? So we have to think about collectively, you cannot do think separately, right? So that potential actually is given in the middle, right? Now we have taken H3 system, so that means H plus H2, again it is products are also H plus H2. So this is a thermoneutral system in both cases. Then this the whatever the potential here and potential here, they are going to be same, right? But in between when they come closer, you can think of the potential what we basically in terms of the curve, if you look at, right? So if this is going to be the reaction coordinates along this, so that means I'm going from reactant to the product. So that is Rxn, so that is reaction coordinates in this direction, and this is potential if you are thinking about. Then in a two-dimension plot, if we go from reactants to the product in a thermoneutral case with a barrier, of course when they come closer there might be a barrier. So what we do, here is my reactants, here is my product, and then we connect through the, so this is getting problem. So it's kind of barrier like this, so same energy. So this is thermoneutral, and this is the, we say this is called the kind of tension state. Right. So dagger we can say, so this is like this is tilted. Right? Okay, so that is going to be we call this is tension state in a tension state theory. So reactants to the product, and then we are going to tension state theory. So when you go from reactant to the product, then there will be a barrier, and finally we go to the product, right? So that is for the potential energy curve. If you plot in two dimension with respect to reaction coordinate, you are going to get a curve like this. This you are pretty familiar with this, right? Okay, so with this much about the potential energy for the, I will stop here today, and we'll discuss if we have any question.